Good morning, everyone. Good afternoon, good evening. For those of you in Europe and Asia, my name is Daniel Melling. I'm the Director of Marketing and Communications at CTrees, and I'm pleased to welcome you here today for our first webinar of the year. CTrees is a science and technology nonprofit that measures carbon in every tree on Earth. We were founded in 2022 and are based in Pasadena, California. We research and develop advanced data solutions that power policy and investment in nature-based solutions in partnership with government agencies, Fortune 500 companies, carbon market standards, and leading conservation organizations. We're really grateful for you to be here today for our presentation, From Snapshot to System, Building a Global Above-Ground Biomass Monitoring Framework. This webinar will explore the science and cutting-edge technology that is enabling continuous global monitoring of biomass, the trees, shrubs, and vines that are vital components of ecosystems and our global carbon cycle. Our presenters today are Sassan Saatchi and Yan Yang. Sassan is CEO and co-founder and chief scientist of CTrees. He is a senior research scientist at NASA's Jet Propulsion Laboratory and an adjunct professor at the Center for Tropical Research at UCLA. With over 30 years of experience in remote sensing of tropical forest structure and biodiversity, he's authored over 300 peer-reviewed journal articles. His work has significantly enhanced our understanding of tropical forest carbon and water cycles, as well as how biodiversity bolsters ecosystem resilience to climate and land use changes. Yan Yang is a research scientist at CTrees. She earned a PhD in geography from Boston University and has conducted postdoctoral research at UCLA and NASA JPL. She is the carbon science lead for CTrees, where she has led our efforts to map carbon on land, including the AGB product presented today and data in our jurisdictional MRV tool. So for the outline of today's webinar, we will have about 30 minutes of presentation covering CTrees and our work on the global carbon cycle, mapping above-ground biomass dynamics, and use cases, including in science and market and policy applications. We will then transition to Q&A, so please put your questions in the chat. We will try to respond to some of these in real time, and we'll address others live. And I will also thank you to those of you who submitted questions in advance. Those will also inform the Q&A period. This webinar is being recorded, and we will provide a link after the event and share the video on CTrees' YouTube channel. I'll now hand it over to Sassan Saatchi to begin the presentation.
Thanks, Daniel, and hi, everyone. Good morning, afternoon, evening, wherever you are. I would like to start the presentation by the role CTrees plays as one of its activities in the global carbon cycle. And this is a picture that was published in 2021 and is a new update version of it in review in Nature. And it basically shows the global carbon balance from fossil fuel going to the atmosphere in CO2 per year to what remains in the atmosphere and what gets absorbed in the ocean. If you notice the land in the middle, it's a large emission to the atmosphere. These are gross emissions, not net emissions, and they become almost half of the fossil fuel emissions from deforestation, degradation, and fire, and few other activities. And the sink in the forest is also extremely large. And this doesn't even include the soil component. And almost 70 to 80% of this exchange of land from atmosphere comes from forests and trees and woody vegetation. So our goal has been always to make sure that we can quantify that piece of the global carbon budget, which is large and extremely dynamic globally. And so we have a series of products that we have produced, and you would hear about the carbon maps today. Above ground live forest biomass or vegetation woody biomass is extremely important. So we have the time series of that. We also have produced soil carbon at 30 centimeter and 100 centimeter, which is due out in publication soon, and also mangrove and blue carbon, both at the vegetation and the soil. We also look at the attributions of changes that are happening to these carbon components on the land. And then land use and land cover change is extremely important. We have products on global deforestation, degradation, secondary forest mapping, and then we also created something on the alert of the land use change globally on Luca and Red AI, which also quantifies fire and logging degradations. We've produced productivity, and this is something that is coming up this year on forest productivity. This is a work we collaborated with TNC, and there is a new version of that at a higher resolution. And then we also produce data on the tree level to basically account for all the carbon at the trees across the landscape, including urban areas. So in general, CTrees using these suite of data sets provide information for global assessments at the level of what countries and national they produce and deliver on UNFCCC, and IPCC uses that data sets to understand the global carbon budget. We also provide information at the national and jurisdictional level to help for both emission reductions, to meet the NDCs and commitments to the Paris Agreement, and also at the local level and projects and also carbon market. So these are the suite of activities we support, and we produce data and operational data set for them. So today we're going to talk about mapping global above ground biomass dynamics. And the products that we're introducing is a 100-meter resolution at 1 hectare globally. It covers 26 years annually from 2000 to current, and it gets updated every year moving forward. It covers forests, woodlands, and savannas, all the woody vegetations globally across the landscape. So in order to start this presentation, I would like to basically start with 3 questions. And the reason we're questions is both measurement, estimation, and mapping are used interchangeably in the community a lot. And they are not exactly the same. And they vary differently. And there is a large variations in biomass products that are generated in terms of mapping, but not necessarily estimations or measurements. So I have 3 questions that why we need to map forest biomass or in general woody vegetation biomass, and why we should do it now more than ever. And the second question is, most of these mapping or estimation requires a large number of what we understand on the ground, the vegetation and forest carbon is, or we measured it with the kind of best techniques such as the airborne LiDAR data sets. And the third question is at what scale we need to map, and why that's important, both in terms of detecting the spatial variations, but also temporal variations. For question 1, I have just one slide. The picture you see on the global Earth and those colors are basically the disturbance data from 2000 to present globally. And this is derived from Landsat data sets. It shows basically where on Earth you constantly have disturbance. The intensity of the color shows, pixels being all covered by disturbance. And you notice that most of the vegetation globally are disturbed continuously. But there is something interesting about this disturbance. First of all, if you look at the figures below, which says distance in area, most of these disturbances happens very close to, they're a small scale. And if you look at tropical and temperate forests, the tropical or the left one and temperate is the right one, majority of the disturbances are happening from 1 to 10 hectares on the landscape at any time. And this is basically analyzing the entire time series of Landsat data set. The other thing you notice that most of the disturbances happening very close to previous disturbances. The distance in 1 kilometer shows that almost in some cases across tropics, 100% of the disturbances are happening every time, almost within a kilometer of the previous disturbance. In temperate forests and in boreal forests is a little bit larger. But that tells us that disturbance or land use change activities on the ground are not a random number generator. They really have patterns, and they occur on the landscape at different levels of the forest. So this tells us that if we have numbers in terms of large scale carbon estimations, and if we try to calculate the emissions, as the resolutions of the areas that we have at the national, jurisdictional, or even large pixels increases, we start having bias in estimation of emissions. And these are for different type of biomes globally. It tells us that the best estimation usually comes in terms of emission where the biomass is exactly provided at the place where disturbance happens, especially for annual accounting. Most of the inventory data globally is done over 5 or 10 years through stock change. But for attributions and emission calculation annually, we need to have disturbance and biomass at the same level. So we need to map biomass globally. The next thing is most of the training data we use, it comes from the ground information. And ground data sets is not completely the truth. First of all, measuring everything, sampling the ground is extremely important with the plot data. And where we sample is also important. So if we want to cover all the vegetation. So there is a lot of uncertainty in sampling. And some of the best inventory data sets globally, such as US Forest Service, have one plot, which is 1 acre approximately every 5 kilometers square. So that's that density they have. In some ecosystem, that density should be much larger. The next thing is when usually biomass is estimated on the ground. And if you want to measure it, you have to basically cut the trees, weigh them, and get that harvest measurements. And then from those measurements and the data that you collect on the ground on forest structure in the plots, you develop allometric equations. And there is uncertainty across the board for all of these elements. So measurements and estimation on the ground is not completely truth. It has its own uncertainty. And it's very important when we are trying to map what type of data sets to use to train our mapping system. This is some examples of the errors that you would see. Allometry is a regression model. So the number of trees helps a lot for that error in the regressions go down. So if you have larger plots or larger number of trees, usually the error goes down to much smaller than 10%. This is an example of the allometry error. When you add height, you add wood density, and you add wood density and diameter. And these are some examples of the 1 hectare plots errors, which is close to plus minus 10 to 15% with the best equations done in tropical forests. And you can see that the plot size is extremely important to really reduce the uncertainty. So when we use data on the ground to train our models or remote sensing data, it would be important that that data is high quality and the biomass estimation has lowest uncertainty. Nowadays, there is a lot of effort to improve that. This is an example of how terrestrial laser measurements, which is cheaper than sending people to the field, but also time consuming in terms of processing, has helping a lot to improve the allometry, both at the species level, and at the same time at the level of allometry overall. This example here shows that the TLS data set helps a lot as the DBHs become larger and larger, especially across the tropics where there are irregular diameters with the buttress trees. And the nice thing is the TLS data matches very well with the harvest data in terms of developing allometry. So that can help us to improve across the board. However, the use of TLS is still extremely limited in the ground measurements. But programs such as CTrees, which is led by Smithsonian, helping the satellite biomass estimation techniques. They're using that on the ground to create a series of data set. The next thing is always question at what scale we really should map. You've noticed that there are maps from 10 meter to 30 meter to kilometers across the community. So if you look at the LiDAR as basically the best approach, airborne LiDAR, to estimate biomass because it gives us higher resolution. And this is an example over a 50-hectare plot at BCI in tropics to demonstrate that. So if you divide the plots at 25 meter or 30 meter, the biomass variation is extremely large because the plot has maybe one large trees, and that becomes extremely high biomass. And then the range of height hardly changes, but the biomass changes a lot. And the relationship between LiDAR and the biomass is extremely poor. And that's one of the reasons that the biomass actually has a very skewed distribution, such as gamma distributions, but the height remains very normal distribution. So it's actually tells you that height at these scales are not a good representative of biomass variations. As you increase the plot, you go to 50 meter by 50 meter, your biomass skewness reduces, it approaches normal to the level that the LiDAR becomes normal. And the relationship also becomes better. And if you go to 1 hectare, then the relationship becomes really well. Your biomass becomes almost normal distribution on the ground. Your height metrics from the airborne LiDAR becomes also normal distribution. That's why the ALS, the airborne scanning LiDAR, mimics the basal area, which is the most important variable to estimate the biomass. So in general, forest is extremely dynamic. If you use larger scale, like a 1 hectare, you can have better relationship with ground measurements estimate. You can also have better relationship in terms of airborne LiDAR data set that you use. And also for change detection, if you see these two images of the LiDAR, airborne LiDAR over BCI, this is taken in 2009, this is taken in 2023, and the average height, the MCH, which people use for estimating biomass, and I showed it in the previous slide, it just has a very small change over this past maybe 14 years. And even though you see a large gaps has been created in the canopy and some trees are grown, but the average change of the biomass is extremely small and the height is extremely small. This is almost at the range of the errors of the allometry and our measurements. So extremely important for even change detection, look at the scales which are reasonable to do this thing. So that's why we actually started doing the biomass mapping at 1 hectare instead of going at 10 meter or 30 meter, because the mapping and estimation becomes really, really close to each other. And then there is a more robustness in terms of also seeing the dynamics. So our methodology has 3 pieces. Module 1, basically, we mapped the forest structure because now we have satellite data sets such as JEDI and ISAT2 provides a lot of information on forest height metrics. And these are still important, at least at the landscape, to provide measures of the biomass globally. So the first module does that and creates a global map at 100 meter of height metrics for the year 2020, which is our base line time that we use for mapping. And then we take those and then put it in another module, which is the second module, to create a global base map of above ground biomass for the year 2020 again. Now, these maps then would go to the third module that uses a time series of satellite data sets and a change detection approach to create time series of the biomass map at 100 meter resolution from 2000 to 25, and then would also gives you the pixel uncertainty. Now, if you notice in these modules, we have, in each case, we use a slightly different approach. Here we use the boosted tree machine learning techniques We develop it at different ecoregions. Here we use a dense net approach for biomass, which gives us a much better spatial variations. And here we also use a temporal boosted trees to really create these data sets. And I'm going to go through these things one by one. So the first step is when we are doing these global maps is, do we have a high quality data sets to map? The satellite data sets have their own issues. Optical data have cloud cover. Radiometric corrections are extremely difficult sometimes for haze, cloud, and atmosphere. And then, so usually you get annual maps or multiple maps different times, but they don't really give you a signal of ecology, both spatially and temporally, to really do this unless you go through the heavy big data processing. And this is what we developed. So we've basically created these time series data ourselves, including both optical data sets and radar data sets. So that's a major effort for building this pipeline. The second thing is putting together a global data sets to train all the machine learning data models. So we acquired a lot of ground plots globally. These ground plots come at different sizes and different regions of the world. Most of the tropical ones we use at 1 hectare. Some of the temperate and boreal ones are small, but we test those things to be falling in a very homogeneous areas, so such that they would represent a larger areas of 1 hectare relatively well to basically include that. So we filter a lot of data sets after we collect these. And the next thing is we have access to huge airborne LiDAR that is collected over different time periods across the tropics. I was involved in both the Amazon, Congo, and Borneo LiDAR data collections, and there's been a lot of data also in US through many projects and in Europe. So we also acquired that recently. A group led by Jonker has published an atlas of all these LiDAR datasets, and these are all available publicly for everybody to use. And then comes the methodology, how to integrate these things. So the first approach for height, we use both JEDI data and ISAT-2. ISAT covers all the boreal zones and a lot of low vegetation areas, especially the woodlands and savannas, where JEDI has hard time to detect the height very well. And then we tested different ways of actually estimating height variations. So we aggregated all the heights at 1 hectare by 1 hectare. So in 1 hectare areas, we have a minimum of 3 shots of JEDI and also the ISAT data set. We built a model that for each ecoregion is different instead of using one global model. So it helped us a lot to reduce the bias and also and improve the estimations. So out of this came out these height metrics and then a cluster of all these heights. The cluster helps us to create these similar type of regions when we go to the biomass estimation, so we can also build multiple models there. So this is the global height maps, and you would have access to this to look at it. It shows the variations of height across the board globally. There are always limitations in terms of very, very high forest areas, such as some of the tallest trees in California. However, at 1 hectare, because of the gaps in the average or mean top canopy height becomes more reasonable. So therefore, saturations that you see usually at 10-meter or 30-meter data does not show up here. And if you look at the results, it basically for different height metrics are here. So this is one model globally, still really good, but has some bias and spatial variations within each biome. It's just not as great. But when we go to 800 models for all the biomes globally, we improve significantly, reduce the bias, and also have a much better variations across the landscape. So the second model is to estimate the above ground biomass. So we use these height metrics and also satellite data. We go to a dense net type of convolution neural network approach. We include all the above ground biomass data sets that represents 1 hectare. And we also include all the ALS above ground biomass estimations at 1 hectare to this to create these global map at one time, which is the year 2020. And we also create the uncertainty of that. So without going to a lot of details, I'll show you some examples how this is important. So first, from structure going to biomass, there is no one-to-one relationship. Height doesn't necessarily always represent the variations of the biomass very well. In some of the homogeneous areas in temperate, even age forests or boreal forests, that's the case. But I'm giving the example of the Amazon because there's been so much debate. What is the patterns of biomass variation across the Amazon? So this is the height variations that you see comes out in a lot of in JEDI data sets and also in our data set. But a lot of biomass maps also shows exactly the same variations. This variations when gets mixed with a lot of other things that happening across the forest, and I can show you more in terms of productivity in the central Amazon is usually low, therefore the biomass is low, productivity is high here, but there are a large number of palms on the western Amazon compared to eastern Amazon. Eastern Amazon has Guiana Shields has larger tree diameters, and the wood density is another culprit here, which multiplies the volume to really creates the biomass. And the variations of wood density from Western Amazon to Eastern Amazon can add another 10 to 20% differences in the biomass for the similar type of a structure. And so that basically changes the patterns of the biomass. And we can see that on the Congo Basin and others. So we use wood density in other to adjust the allometries that we use for these LiDAR data set or ground data to include in our biomass mapping. The validation is here. I'm going to show you a few examples. The paper would give you all of these details. This is done over all the biomes globally for biomass. We compare it with the plot and LiDAR estimated AGB. And we just use a large number of those things. And the results is really good in terms of the average. For each of the biomes, the results can be much better. But globally, this is the case. And if you look at over the tropics, you also have across the tropics really good results in terms of the RMSE, in terms of the bias as well. And we've done to process bias correction in different steps at the different levels. So that's the results to see globally. And then when you compare it with the LiDAR data, you also see significantly good results across the board. And because this biomass ranges all the way to 500 to 600 tons, but most of the biomass globally remains at the lower level because of the dominance of temperate or boreal data sets. And then when you collect with the plot data, compare with the plot data, because there are 1 hectare plots, but some areas there are smaller type of plots used, like half a hectare or an acre, especially in the temperate and boreal zone. The R score is a little bit lower, but however, it shows significant comparison agreement with the distributions of plots globally. If you look at regions specifically like US, which is we are very much interested, you can see these time series data sets and compare it with any time you have the FIA plot data at the county level, because the locations of FIA is not known. We had these data set before, so we developed a lot of model on this. And so you get really good results when the number of plots in the county increases. So that tells you that sampling is extremely important to get the mean right. This is a result just recently got published by the California compared their plot data with some of our maps and published it in the report. And I just took it from that to show that there are a few other maps that they have compared. All of them showed really interesting results and good quality results over California. Last but not least is the change, which is probably one of the most difficult parts. So there are two ways doing that. Just taking the satellite data mapping every year. However, that can create a lot of noise in the data sets because the changes can be chaotic because the temporal data set is extremely noisy. So we developed an approach that actually, first of all, training data is also important. We don't have a lot of LiDAR or ground data repeated measurements globally to train this model. So in order to do that, we created some innovative approach. When we have the biomass map for 2020, you can see the biomass of a location here in pixel A and location B pixel, another pixel, have differences. And that differences translates to the depth of the data sets used to predict those. So you look at data sets from 2020 and 21, and within the spatial variations, create these spatial differences of biomass and relate that to the temporal changes. And then take the stack of data that shows that temporal changes, create a large number of training data across the time to run this model. This is another AI generated a methodology that tells you that how the differences between 2 points can be actually translated to differences over time, because especially when you're looking at the disturbance and recovery than actual biomass in the old growth forests. So that large number will help us to do the change detections. And we also do a lot of post-processing, clamping the anomalies that comes for each pixels. And then you get images like this. This is just showing 3 years in RGB. So you can see a large areas which are kind of gray or white means it hasn't changed, but other areas has changed over different times. And then there is elements of regrowth, the blue areas that shows up. So you can actually classify different type of change that happens on the ground. So if you look at these similar pixels, zoom in, there are times that there is earlier deforestation and they remain deforested, and you can pick up in the time series data set. Those are areas that are red. That means in 2000 or early years, they were high biomass and then gone down. Sometimes the change happens not abruptly and episodically, but over time. And you can see that in some of the pixels that are kind of orangey, that the change of biomass reductions has happened over time. And then sometimes it happens at the later year, the change happens, and we can detect those variations easily. The same thing goes with the growth. There are times the blue areas and these RGB is the later time. There shows growth. So there has been areas that has low biomass and then it started growing and going up in a matter of 5 to 10 years. You suddenly have 50 to 100 megagram of biomass generating, especially in the tropics we are looking at. And then the growth can be also going up slowly and then going down, and then, or the deforestation happens and remains deforested, such as the secondary forest, and then it starts growing and over time. So that's extremely important. So if you look at the time series data, you can see these variations across the landscape very well to see especially the disturbance in deforested areas shows up, and then a smaller scale regrowth shows up. So for use cases, it's extremely important to look at these data sets. First of all, globally, we can have pictures or patterns of the changes of areas that has been reducing in biomass and areas that has been growing in biomass. And this is just showing 2 dates from 2025, 2015. But the time series can give you trends of growth and trends of reductions of the biomass. But locally, at the jurisdictional level, you have a lot of opportunities to use these data sets to create emission factors and to apply that for different type of disturbance here using fire at different biomes in the Mato Grosso in Brazil, where you have the Pantanal biomes, you have the Cerrado, and you have the Amazonian, and each of them have been hit by fire. So if you look at the above ground biomass before and after fire, on average, you can see these changes that is happening across the board, and can be good for emission calculations and also for accounting of carbon. At the local and project levels, you can also see that. This is just an example of the California, where you have these logging that is basically clearing the land, and you can see that huge reductions and then gradual growth over time across the board. So there is some level of reductions on average. This curve is for the whole area, but for each pixels, you can see the changes more abruptly. The same thing goes for this area in southern China, where you have a huge plantations and growth of the forest, and you can see steady growth of the biomass going from 2000 to almost present. So these are the afforestation projects. So even though it's 1 kilometer, I mean 100 meter, but the time series is extremely robust and accurate to show you these changes that are happening at different scales. And this is for very small local projects. It's a secondary forest, similar to, afforestations and ARR type of projects in the Amazon. So this area right next to this deforestation is growing, and you can see that gradually the biomass growing to all the way to close to 140 megagrams. The biomass growth in the early years sometimes is lower, and in the mid-age, it becomes much better. This is shown in the paper that we just published with the TNC group recently, and it's coming out to show exactly how productivity from early age to later age changes. So it captures these changes over time. So to conclude, our biomass approach, going from a snapshot to a system, creates these uh, framework that allows us to kind of map biomass over time, and then also constantly improve it as data becomes better, and as also our understanding of biomass variations learned from ecologists and other people who collect data on the ground improves. Another thing is, the space agencies are also been working hard to make sure that carbon quantified much better. I have been involved in both NISAR from NASA and biomass missions for the past 15 years that took to launch them last year. And the data are becoming available now as we speak. And NISAR gives us a global coverage, almost weekly data set. It captures dynamics of the vegetations in the low to mid biomass for all of the temperate and boreal forests and a large number of secondary forests across the tropics. And biomass missions mainly focuses on the tropical areas. These are the regions that the biomass covers mainly. And it gives us estimation of biomass for really high biomass areas. And then we also have JEDI that is collecting data, giving us a lot of forest structure. And JEDI is also producing biomass at both a shot level and then the coarse resolution and ISAT2. So we have a suite of data set that we can use to improve these biomasses over time. So having said that, the data set that we produced here, we're making it available freely to the community. I think it's important for the community to use these data sets, gives us feedbacks, and use them for a lot of use cases, both scientific approach at the local and global level, jurisdictional level, emission reduction activities, and also any use for the market, both in terms of improved forest management and the ARR approaches and RED projects globally. So we are giving the data set in the Earth Mover. I think Daniel is going to cover this piece for us, the details information. Just to let you know that the data sets, everybody can log in and just download the data set from Earth Mover. And we are also planning to release the data set across the board through different venues. CTrees would re- release it. And also, we are working with a lot of carbon registry groups and also a lot of other platforms such as Google Earth Engine to have the data available to the community. I'm going to stop here. Daniel, do you want to follow up on this?
Great. Yeah. Thanks, everyone. We're really excited to announce the release of this data set today. I'm seeing some claps and hearts in the chat. So thank you to everyone for your response. The data set is now available via earthmover.io, and you can set up a free account and you can subscribe for the analysis ready cloud optimized data. We'll also be sharing in the chat here a tutorial document via Google Colab that allows for Array Lake and Python packages where you can query the data, conduct analysis and visualization. So we're really excited to share this with the community. It's under a Creative Commons license, so you can use it for any application. We're also looking forward to your feedback. And you can always reach us at info@ctrees.org or via the contact form on our website. There's also contact details on the Earthmover product page. And so we'll be happy to hear a response, how you're using the data, and how it can help your research and applications. Are you ready, Sassan, to transition to Q&A?
Yes. I'm going to stop this and so I can see.
Great. So we've had a number of questions. Some of you submitted in advance, and others are coming in live via the Q&A. I think there's kind of three categories. One is around the methodology. A second is around access to the data, which we've just discussed, and also applications. So how does this work for kind of policy and carbon projects? So we've talked a lot about the methodology. So I thought maybe we just discuss some of the applications first. So we had a question from ACR at Windrock International, which is how close or far away is this technology from being integrated into existing methodologies for improved forest management and ARR, which is afforestation, reforestation, and revegetation.
I think it's very ready to do that. And I think there are two reasons for it. One reason is actually, and I'm also not promoting CTrees data, but also promoting a lot of other data sets that may exist and may have high quality in other regions of the world. I think using these maps is extremely important for accounting, for estimating the emissions and estimating the removal accurately, especially for RED projects, improved forest management, and also ARR. Now, ARR at a smaller scale may have issues with the detecting early stages of growth. So usually my recommendation is these global products, which we still call them off-the-shelf products, even though they're validated, they can be used a lot for feasibility studies to get the first carbon accounting done scientifically, and also help to see if there are issues to go directly to do customize for local areas. As we go locally and develop our models at the local level with maybe additional data set, that customized results are going to be much, much better in terms of the quality. So I think my recommendation is these carbon registries and methodologies should use these data set as much as possible. Especially these are ours is free, but in general, this reduces the cost of doing a lot of ground measurements. And tell you the truth, except the research plots that exist globally or some of really established inventory plots, such as US Forest Service, a lot of plots generated rapidly on the ground and small plots do not have really high quality. And they have been also an issue with a lot of projects and carbon credits. So my recommendation is use the maps at the local level or these global maps as much as possible.
Great. And I have kind of a related question. We're just going a bit more into specifics. Do you have anything to say about using the maps for understanding plantation, including younger plantations? We had a question from Tist about this. And a related question is this method different from MOFUS, which is modeling fuel wood savings scenarios? And that question was from Gold Standard.
So, first question, yes, use it for plantation. If the plantation areas are large, we've done this tests over country of Gabon, where we have these large palm oil plantations. We've captured the biomass very well, and you can see the time that land was cleared and plantation has gone in. So for larger scale plantation, it works really well. You have these monodominant eucalyptus trees planted in different areas. You can see that as well. So that's, yeah. The second thing is, I think I know about Mofus, and I actually work with the Mofus team on the cook stove and of wood fuel. But in general, models are not able to really capture biomass on the ground. There is a huge variability, and it's very difficult to really get that. So I think biomass has to be estimated either on the ground or through remote sensing data and mapped. I think a lot of areas that people have worked extremely sophisticated models, and they usually give you some mean variations spatially and temporally. It's very difficult to get those things working and match the reality.
Great. Thank you for the response, Hassan. Um, I'm going to go back maybe to a bit more on the methodology and also thinking about what makes this data set unique or different. So we had a question from Lin Xiong at University of Maryland. How is the global biomass mapping in CTrees different from the European Space Agency's Climate Change Initiative biomass project?
Well, our methodology is significantly different from them. So that's one thing. They used originally mainly using ALOS data sets to create biomass, and then at the low biomass levels up to 150 megagram per hectare, and then using other satellites to combine those things with machine learning. So it's a slightly different approach, and they're a great team. They're doing these things, and one thing we have done, which is extremely different, is we have built a platform that consistently look at changes. So the change detection method is extremely different than what they do. Apparently, the CCI maps so far, and they may change also the method because it's a really good group that works in Gamma to develop these. They do every year separately, and the dependency on the ALOS data in terms of quality is really depends on that. We've been using a huge time series data set to really create this data. So I think in that sense, in terms of change is different. Uh, People have to go and use these data sets and look at their own areas and to see exactly how accurately they do. I think in some areas, probably we're doing similar estimation accuracy. In some areas, it might be different. There is a whole suite of activities on map comparison, but you can say the same thing, suite of activities on ground estimations. We have worked in the projects where one team went and collected measurements and another team went measurements, and the two estimation on the ground were significantly different, and that really impacted the projects, the carbon projects that we were working on. So I think there are variations in maps and in these estimations, and scientifically, I think we are always in improving. We learn from the European team, we learn from other commercial data sets that are available and people using, and then incorporate that. So I think we need to think about it as something that evolves and gets better in future.
Great, thanks, Hassan. I want to come back to we've had a few questions around validation and ground data, so I'll kind of summarize, but I think one of the questions is um, kind of the differences between the availability of ground data in tropical and subtropical regions in Africa, in India, and also in the US. So how can you say a bit more about how the availability differs between different regions and how that impacts the AG estimates for those geographies?
So I think there are three types of ground data. One is the forest inventory data. And although these are done kind of with a nice sampling design to really get unbiased estimates over large areas, such as the US Forest Service that has close to 120,000 plots in the forest and much more in the non-forest areas. These plots are reasonably large. They're like 1 acre for the temperate forest. And they've measured, they're permanent plots. They measured every 5 to 10 years, depending on where you are. In the East Coast, it just repeats every 5 years. In the West Coast, it's a little bit slower because of the access and other issues. So those inventory plots that is coming from these regions are really good. Now, you still have to filter them because if the variability is large compared to your pixel, you may introduce errors in terms of both training and validation. The shape of the plots is also extremely variable. So people use long transects across the or circular plots, and all of those things adds additional errors when you compare it with your map because maps are pixels and they depend on the geographic projection. The second type of plots are these, especially in the tropics, are these plots that comes from research communities, such as the Smithsonian Center, such as Rainfor, Afritron, and GeoTrees. And these are extremely well-designed plots. They are large, first of all, from 1 hectare to 50 hectare, and some cases much even larger. There are detailed measurements done by ecologists, botanists, and these measurements are really high quality. And they're much better than inventory plots because the inventory plots are designed such that at the locations they have large errors, but at the end ensemble, the error goes down. So if it's good to use them at the regional uh, comparison and estimation. Whereas these research plot at 1 hectare, it has 10 to 15% error and so hard quality. Then there are these other type of data sets that comes in haphazardly through some projects. And you need to really look at the quality of those to see if they're good to incorporate and stuff. And the availability is also different. So some people don't like to share the plots. They just only give you so you can use it for your approach and then for co-authorship and stuff. So it's extremely variable. A lot of inventory plots are not available for the public unless you develop a memorandum of agreement, you protect them, you never distribute them. So it is really challenged. That's why airborne LiDAR data sets for collecting and large areas and calibrating them with the plot data becomes probably the best asset to create maps in future.
Great. Thanks, Hassan. I'm going to ask one more methodology question, and then I think we can talk a bit more about applications. So there was a question from Yufang Ho at OpenGeo Hub. What do your product uncertainty look like in the time series? And how do you approach quantifying uncertainty?
We didn't have time to show. First of all, there is a spatial uncertainty and temporal uncertainty. We've done a lot of filtering to make sure that really, you know, anomalous data sets like really high up and down goes. Because remember, you take the satellite data and sometimes, especially the optical data, is sensitive to greenness. So you might have a greening vegetation that hasn't really changed the biomass, and then that would change your signal. So time series data allows us to really make sure areas that um, are intact forest, there is no disturbance so much, those are close to each other over time. So we create these filters and constraints ecological constraints, we call them, to make sure that's the case. We will provide a huge uncertainty estimate for these from the data set that we have developed. But it's very hard to do that with the plot data because there are, except some of these permanent plots across the tropics at different times, and you need to match your timing of the map with those. Especially, we can do much better. I think especially there are two levels. At the pixel, the uncertainty can be large, can be sometimes 20 to 30%, especially when you go to the rainforest. And you've seen the examples I showed from the allometry on the ground as well. So they can be also 20, 30%. But the nice thing is, as you aggregate, the uncertainty really goes down. We've shown a large number of examples through publications the past few years, how the maps should be used and how the uncertainty has to be calculated for your project area, for your jurisdictions. And these maps becomes extremely important. So because instead of like, a few hundred plots, suddenly you have 1 million pixels, even though there is an uncertainty larger than plots in these pixels, but that reduces the error and a lot. So if you can take care of the bias, you have unbelievable precision in your biomass estimation, spatially and also over time.
Great. Thanks, Hassan. So we have a few minutes left. I'm going to ask kind of one more question, and then we'll kind of just close with some final thoughts. There's a lot of variation in biomass and landscapes, and we've had a couple questions about how the AGB maps perform in urban or developed areas from Alex Young at University of New Hampshire. Also, the performance for agroforestry applications. Question from Jeffrey Vincent at Duke, and also in the margins between forest and non-forest areas. That's from Aaron Berryman at USDA. So can you address kind of how the maps capture these variations in different landscapes?
Okay. First, the margin. I think even though it's 1 hectare, and we have a paper a few years ago by one of our postdocs across the tropics showing the edge effects between forest and non-forest has significantly lower biomass and because of the mortality increases. Our maps really shows that. And that's one of the reason I brought to show that mapping versus is extremely important because if you go and do old growth forests in the intact forest and not look at the edges where the next deforestation happens and the biomass is usually lower, your emission factors would be different. So we capture those really well in most areas, and we've tested that. So that's one thing. Now, in terms of agroforestry, it's a difficult question. I don't know the answer yet. In some areas, since agroforestry system can be really small scale, a mixture of trees and natural trees, and then fruit trees and other agroforestry plants, it might be difficult to really get. And we really do not have data, at least I don't have data globally, where these agroforestry systems are. There are some maps here and there, but in the areas which agroforestry is open, such as, you go to Ghana, a lot of cacao plantations and coffee, you can see the changes of the biomass because even though some of these are shaded forest, in the optical data sets, you may not see the difference as much. But since we've used radar in our approaches, we capture these differences very well within the agroforestry systems. So we need to kind of find out exactly how well we are doing. But visually and also capturing areas that we know that it looks good.
Right, and urban and developed
Oh, urban
areas?
is tough. Urban areas, that's why we use the very high resolution data set at the tree level. I mean, you can see in the urban and wildland interface areas, which there is more vegetations. Like we worked a lot in California, especially in the Southern California with chaparral regions. We captured those differences very well, even though hardly any measurements on the chaparral in terms of the carbon estimation. We capture those variability very well. But when you come to within the cities, I think you need to have much higher resolution data. That's where we have our tree-level data sets. We've created 1 meter and 5 meter estimations of tree cover and height for these areas, and using allometry in the cities to create the approximate biomass of these trees. And it's also extremely difficult in urban areas because people prune their trees constantly. They don't follow any allometry. It's just difficult. So it's extremely approximate.
Great. Thank you, Sassan. We're now at the top of the hour. So I just want to say thank you to Sassan and Jan for the presentation, and also to all of you for attending. We really appreciate your interest in this work, and also your collaboration, questions, responses. The goal of CTrees is both to conduct advanced science and develop new technologies, but also really to create operational data sets for real applications. So we want you to use the data set on Earthmover, explore it, and come back to us with any feedback, ideas, and suggestions for how we can really put this into use. So we'll be following up with an email with relevant links and more information. And we'll also be posting the recording of the webinar for everyone who wants to go back and learn more information. So with that, I'll close the webinar. Thank you again, everyone, for your participation, questions, and feedback. Okay.
Thank you.